Welcome everyone for today's class. In this class, we are going to discuss about precipitation from homogeneous solution, digestion of precipitate, and sequestering agent or masking agent. So these are the three things we are going to discuss in this class. First, we shall take precipitation from homogeneous solution. What is precipitation from homogeneous solution? It is defined as it is a process in which the precipitant is slowly and chemically generated in the reacting solution itself. So which means it is a process in which the precipitant is slowly and chemically generated in reacting solution. So this is called precipitation from homogeneous solution. Let us take an example and discuss about the precipitation from homogeneous solution. For example, we take barium ion. Barium ion is precipitated as barium sulfate by mixing barium solution and a solution containing a calculated excess of sulfamic acid. Here we are going to precipitate the barium ion as barium sulfate by using sulfamic acid. The formula for the sulfamic acid is NH2SO3H. In this precipitation, sulfamic acid, the sulfamic acid solution slowly generates sulfate ions in solution by hydrolysis. When we so it combines with water molecule and it generates sulfate ion like this. These SO4 formed SO4 ion in the solution react with barium ion and form barium sulfate. So which is precipitated, and also by using dimethyl sulfate. So the formula for dimethyl sulfate is using this dimethyl sulfate. Also we can, by using this also we can precipitate barium sulfate, can be precipitated by using barium sulfate. Barium ion combines with this and gives barium sulfate, and we can estimate by using the amount of barium sulfate present in uh, barium sulfate. From the barium sulfate we can get the amount of barium ion. So in this precipitation from homogeneous solution, what is precipitation from homogeneous solution? Which means it is a process in which the precipitant is slowly and chemically generated in reacting solution. So slowly generating the precipitate by using some ions present in the solution. So we have discussed uh, with an example. We are barium as barium precipitate formation. We are using sulfamic acid. In the solution, sulfamic acid is converted into these ions, especially sulfate ions, by hydrolysis, and by using this sulfate ion combines with the sulfate ion, barium ion forms barium sulfate. So, by using this barium sulfate, we can estimate barium 2 plus ion. Likewise, dimethyl sulfate. Here, the structure of di- dimethyl sulfate is this, and the structure of sulfamic acid will be like this. So these two things are producing SO4 2 minus and forms precipitate with barium ion. Then we see what are the advantages of precipitation from homogeneous solution. By precipitation from homogeneous solution or the homogeneous media is done, which is to avoid a local reagent excess. It avoids when we are precipitating, um, precipitation is done from the homogeneous solution, it avoids local reagent excess. So if it avoids local reagent excess, the precipitating agent appears slowly homogeneously throughout the entire solution. So if we doing or if we are going to do the precipitation from homogeneous solution, it avoids the local reagent excess as the precipitating agent appears slowly and homogeneously throughout the entire solution. And it the relative saturation relative supersaturation that will be low for this when we do precipitation from homogeneous solution. The relative supersaturation is low, and then this method results, that is precipitating from homogeneous solution, this um, method results in marked increase in particle size, increase in particle size, and also particle size of the precipitate increases. When it increases the size of the precipitate, so it is easy to filter and to dry and to weigh, and also it increases the purity will be increased. Now we know what are the advantages of precipitation from homogeneous solution. So there is use of local reagent, um, it avoids excess using of the local reagent, and it decreases the relative supersaturation, that will be low, and then it increases the particle size of the precipitate and purity. Next we shall move into the another topic, digestion of the precipitate. How what digestion does in the precipitation. So what is digestion? What we are doing in digestion? So digestion is the process of allowing the precipitate for several hours at room temperature of at a desired high temperature in contact with a solution from which it was formed. It increases the and it it maintains the contact between the solution and the precipitate um, at longer time at higher temperature. So therefore, it is the process of allowing the precipitate for several hours at room temperature or at high temperature in contact with solution. That is there is a contact between the formed precipitate and the solution in at long time or several hours. even sometime even for a day. Effect of digestion. What is if we digesting the precipitate? What happens in the precipitation? So we shall see the effect of digestion. If we digesting the precipitate, what it does. Effect of digestion. What it by using by digesting the precipitate. What happens? Digestion promotes complete precipitation in a form which can readily be filtered. So when you are doing the digestion, it promotes complete precipitation so that we can calculate the exact amount of the ion or the substance present in the known solution. And then during digestion, small particles will tend to pass into solution and then which redeposit on larger particles. The small particles is converted into larger particles, which redeposits and converted into larger particles. So that therefore, so when converts, it converts into small particle into larger particles. It promotes the formation of a regular crystal shape. Regular crystal shape will get the regular crystal shape and with lesser surface area, lesser surface area, and also it reduces when it forms a regular crystal shape and lesser surface area, which reduces co-precipitation. It reduces co-precipitation by adsorption. Therefore, the small particles convert into larger particles during the digestion process, which which converts the precipitate into the regular crystal shape and which changes the lesser surface area, and these reduces formation of co-precipitation. And third one is impurities trapped inside. During digestion, the impurities trapped inside the mass of the precipitate escape from their places. So when the impurities escaped from the places, it increases the purity of the precipitate. So therefore, it increases purity of the precipitate. So now we have discussed the effect of digestion. When you are digesting the precipitate, it promotes complete precipitation, and then so when the complete precipitation occurs, the filtering is easy, and also we will calculate the exact amount of ion, and then um, the digestion during digestion the small particle is converted into the larger particles, which is easy the, it it converts the precipitate into the regular crystal shape and the lesser surface area, which reduces the co-precipitation, and uh, impurities present in the precipitate gets escaped during digestion, so it increases the purity of the precipitate. Next we shall see what is sequestering agents. The sequestering agent is a reagent added to eliminate the interferences or the disturbance by a substance in estimation. It is to eliminate the disturbances or the other ions present in, or the ions which will get precipitate during with along with the the ion which is going to estimate is to be eliminated. So to eliminate to eliminate the those ions, we are adding a substance is called sequestering agent. For example, In estimation of magnesium ion, gravimetrically, there is a presence of copper 2 plus ion also. So when you are estimating magnesium ion in the presence of copper ion using oxime, here the precipitant is oxime, then we have to eliminate the copper ion. It should be eliminated. So otherwise the copper may get the precipitate, so that we should eliminate the copper ion. For this we are using cyanide ion. So to eliminate copper ion, which is soluble in the forming precipitate, is soluble in the solution itself. So here we have the copper ion is present in along with the magnesium ion. It will be it is form a complex ion with cyanide and gives, so the four cyanide ion combines with this and forms copper complex. So this complex is soluble in the solution. This copper is prevented from uh, reacting with oxide, so it could not react with the oxide, so it gets avoided. Now here uh, to eliminate this copper 2 plus ion, we have used cyanide ion. This cyanide ion is called as sequestering agent. The cyanide ion is called as sequestering agent. Sequestering agent is also called as masking agent. Sequestering agent or masking agent. This is the purpose of adding sequestering agent or masking agent. Then this process of eliminating an ion or a substance using a chemical agent. So we have used here the chemical agent, that is cyanide, so that it does not interfere in the estimation of another ion or substance, is called sequestration. Sequestration. So we know what is sequestering agent, and we have discussed with an example. And what are the uses of this sequestering agent in gravimetric analysis? Uses of sequestering agent. Some of the uses we can discuss here. The sequestering agent is used in estimation of magnesium. That is, magnesium ion can be estimated gravimetrically with uh, oxime in the presence of copper 2 plus ion. Here it uses using cyanide. Already we have discussed cyanide ion as the sequestering agent. And next uses in estimation of calcium ion with suitable reagent in the presence of copper 2 plus ion using cyanide. Here also the cyanide is used as sequestering agent. By using cyanide we can precipitate, or sorry, formation of the complex with copper ion. And third one is, in the presence of EDTA, beryllium may be precipitated with ammonia in presence of chromium, cobalt, cadmium, iron, copper, lead, manganese, zinc, aluminum, bismuth, etc. So in presence of, so here the EDTA, ethylene diamine tetraacetic acid, here the beryllium may be precipitated with ammonia in presence of chromium. We are using this, we are going to precipitate the beryllium. This beryllium may be precipitated with ammonia. So ammonia in the presence of some other metal ions like chromium, cadmium 2 plus, and then iron, copper, lead, manganese, zinc, aluminium, bismuth. If there are the presence of these ions in the solution during the estimation of beryllium, we can use EDTA as a sequestering agent and we can eliminate these ions. And the fourth one, uranium can be separated from numerous other ions by precipitation with oxide from an EDTA solution at pH 5.3. So uranium, when we are going to estimate the uranium is precipitated from along with, when the uranium is presented along with other ions, we can estimate by using oxide. In this also we can eliminate other ions. We can use EDTA at the certain pH, that is 5.3. And the fifth one, the next use of sequestering agent, copper has been masked with EDTA. Copper is masked with EDTA in the polarographic determination of antimony in alloys. If you are going to determine antimony, if we want to determine the antimony in alloys using the polarographic determinations, here the presence of copper is masked with EDTA solution. And then the next use of sequestering agent is precipitate of soaps as the calcium and magnesium salts by hot water can be checked by transforming these metals into soluble complexes of EDTA. Here, using this, using EDTA, we can estimate the calcium and the magnesium, how much of calcium and the magnesium present in EDTA soap solution. That is, calcium and magnesium ion can be estimated in solution. Therefore, the sequestering agent used in the estimation of magnesium and in the estimation of calcium and in the estimation of beryllium as beryllium EDTA, I mean with EDTA, and estimation of uranium as uranium with oxide. Here we are using EDTA as the sequestering agent. Likewise, in polarographic technique, we can estimate antimony in alloys. There we are using EDTA as the sequestering agent to mask copper ion by formation of the complex, and then it is also used in um, used to estimate the hardening of water. In this class, so far we have discussed precipitation from homogeneous solution, digestion of precipitate, and sequestering agent, and then we have discussed one by one what is precipitation from, how we are doing the precipitation from homogeneous solution, and what is uh, precipitation from homogeneous solution, and we have explained with an example, that is barium as barium sulfate. And then we have discussed the uses of precipitation from homogeneous solution. There are some of the uses of precipitation from homogeneous solution that are the avoids the local reagent, relative super, and supersaturation will be low, and it increases the particle size, and then therefore it increases the purity of the precipitate. And then we have discussed about the digestion of the precipitate. We have defined the what is digestion and what is the purpose of digesting, and effect of when we are doing the digestion, the precipitate is digested. What happens is explained in this class. That is, effect of digestions are the digestion promotes complete precipitation and it increases the particle size, which promotes, that is, a reduction of, or which reduces the co-precipitation, and then it decreases the impurities, so that therefore there it increases the purity of the precipitate, then we can estimate the exact amount of the ion present in the solution. And we explained about the sequestering agent or masking agent. We have defined what is masking agent, and with an example, that is cyanide ion. Then we discussed about the uses of masking agent or sequestering agent, and these are the um, uses we saw in this class. Therefore, I hope you all understood what is precipitation from homogeneous solution, how we are digestion of precipitate and sequestering agent, and what are these uses, everything. I hope you understood. Thank you.